Alright, so this presentation is going to be on our work using physics-informed machine learning to solve a three-dimensional intersecting flow problem, and specifically using domain decomposition and a global dynamics constraint. So to begin, the most common way for us to solve complex or even just regular fluid flow problems is to use computational fluid dynamics, or CFD. However, CFD does run into a couple limitations, specifically when we look at these intricate three-dimensional domains where meshing actually becomes quite a challenge to do. And above that, once we want to do something like optimization, where repeated iterative steps are needed, then the three-dimensional and intricate large meshes that need to be generated for CFD becomes quite a challenge to do. However, CFD is still a pretty dominant method in solving these complex problems. Now, one reason that one might want to use a machine learning approach to solve these problems is due to the fact that it is pretty easy to add more dimensions to our problem. Say if we want to explore a wider range of Reynolds numbers, or to explore um, a larger range of different domain shapes and sizes, then it's pretty intuitive to be able to add more inputs to our network compared to having our CFD methods being solved for each individual problem separately. However, when doing literature review to see what sorts of problems have been solved using traditional machine learning methods, we find that because traditional methods are heavily dependent on data, and there aren't really much that are physics-based. And for the ones that are physics-based, we see that they've only solved these simple flow problems compared to something that's 3D, high aspect ratio, or something that has multiple inlets and outlets. And so that's kind of the target that we're going to be looking at. And so the specific type of machine learning method that we're going to be using is called a physics-informed neural network, where essentially we're able to encode some physical meaning to our outputs. And so the figure shown on the right here kind of shows that we can take some spatial input, run that through a fully connected neural network, and we're able to output some sort of flow parameter, say velocity or pressure. And through automatic differentiation, we're able to build these loss functions here. Here I've shown on top, which is a simple Laplace equation, and some sort of boundary condition to be able to constrain our outputs to have these physical meanings and satisfy these governing equations with these specific boundary conditions. And pins have been demonstrated in a wide variety of physical equations for simulating fluid dynamics and solving inverse problems and these multi-objective problems as well. And so the specific problem that we're going to be looking at is this 3D steady state intersecting flow, where we have flow entering here from the left and the bottom, and then having some sort of mixing interaction here in the center, and then and then exiting from these two outlets here at the top and then on the right. And so our pin here takes in these spatial inputs along with boundary conditions. In this case here, we have no slip on the walls and a uniform inlet here at the left and the bottom. And we want to be able to predict the three-dimensional pressure and corresponding x, y, and z velocity fields. So some of the research objectives that we specifically want to look at is to understand the performance of pins on these very complex and high aspect ratio. And specifically for this case, we have a cross-shaped flow, so there's going to be a lot of flow recirculation and such. We want to see if the pin is able to be able to capture this, and what sort of convergence criteria we need, what error sources exist, and how errors propagate along our channel. And so to begin, we simply used a single network pin for this, and we do see that single network pins actually have a few failure modes. Shown on the left here, we have a long channel where the failure occurs due to this high aspect ratio of the height to the length, and we see that edge singularities actually impact our flow x, y, and z velocity flow results, where the top right corner and bottom left corner exhibit some sort of singularities, where that propagates into our flow, and it shows up within our predictive flow pattern. And going up into our three-dimensional domain here that we're interested in, we can see that the single network pin just fails for all of these pressure and velocity predictions compared to the simulation on the top. And so the approach that we took was to have a multiple domain pin approach called MD pin, where essentially we break down our domain into these smaller subdomains and assign a smaller subnetwork to these subdomains. Now, to ensure continuity across our domains, we impose matching conditions here on the interface, and actually the formulation of this these parallel networks allows us to write our loss as a composite loss function here shown on the bottom left, which is a single loss function that we can do optimization upon. Now, with this domain decomposition method, we build this network, and this network needs additional constraints to be able to be able to be solved. And one of the constraints here is the matching condition. So in order to ensure continuity between these subsections here at the interface, we take the outputs of the network at the interface and set them equal to each other. And so we're only matching up to the zeroth order or the constant order term, so velocity and pressure, and there's no higher order derivative matching here. And another constraint that we found to be very helpful was a global continuity condition here, where we set the inlet mass flow rate to be equal to the outlet mass flow rates, which in theory should be constrained by the continuity equations from our PDE, but we found that that constraint was actually not enough to be able to fully satisfy the mass flow rate continuity conditions, where we actually see some mass leaving from these interfaces here. So this is another constraint that we imposed. So our network architecture consists of 7x100 fully connected neural networks. So these are individual subnetworks. So we can imagine 9 of these in parallel making up our larger network. And we have 4 loss components: a physics loss, boundary loss, and then the matching and system continuity loss that we discussed earlier. And so for our physics loss, we are solving the laminar incompressible Navier-Stokes equations shown here on the bottom left, with our conservation of mass and conservation of momentum equation written out there. So the cross-shaped flow, as I discussed earlier, has these complex recirculating motions that we expect. So we see quasi flow coming in from our inlets here and then deflecting at this intersection region and then exiting here from the outlets. And we can take some cross-sectional views of these shown here in B and C, and we can see that there are very complex recirculation patterns that are essential for this flow. Now we can compare a traditional MD pin, which is a domain decomposition method, versus our MD pin with our additional global continuity constraints. Here, so we've shown 3 different MD pins here. So the first one here is just a naive method, and then the second one is having additional physics constraints through additional collocation points, and we see that additional collocation points indeed help with the prediction results. However, we see that with global dynamics, we can take the settings used for MD pin 1 and add just an additional loss term there, and we're able to get a much better approximation compared to the simulation results. And here shown at the bottom, we see that the global dynamics method improves by 76.2% and 52.9% compared to MD pin 1 and MD pin 2. So now we're interested to see where are the errors coming from, even with this global dynamics additional global dynamics constraint. And we see that here shown at the bottom, there are errors here that make the flow asymmetrical, and we attribute this to the singularities that occur along the edges of our domain. And we see that the largest streamrise errors occur in the outlet sections. That's about 15% or so. And the largest Z component error actually occurs, if we look at the video here, is across this diagonal here where the flow impinges and turns very rapidly, and that causes a very sharp change in the velocity, so a large gradient there. And we also know that large gradients can also cause some sort of instabilities within our results as well. And so to conclude, we see that the domain decomposition method actually helps the network learn much better compared to just having a single network. So having a conquer and divide approach compared to just trying to solve the problem using one single large network. And the global dynamics constraint, so having an additional constraint on continuity actually helps improve our accuracy here between 52.9% to 74.8%. And the errors that we see are just likely due to the corner singularities that propagate downstream and then are more prevalent at the outlet sections. So of course further validations are needed on different sorts of geometries and different flow conditions. And for more details on the network settings and some sort of other things that we didn't really talk about within this presentation, we can refer to the paper that's going to be published in the Neurips 2025 conference publications.